So we are through with one chapter. We are in the middle of the derivatives chapter. I told you at the beginning of the year that there are 3 sections to AP Calculus. One was limits and continuity. The second was derivatives. The third one is integrals. And we are right in the middle of that second part of AP Calculus. So we are buzzing through this thing. You have a test at home with you right now. I wanted to remind you at first, so about some little quiz hints real quick before we start talking about derivatives of trigonometry. The quiz hints that I wanted to provide for you real quick. For 1A, I am looking for all the steps of solving for a derivative using this definition. When it says using the limit definition of a slope, I'm looking for all the steps. I totally know that you know how to take the shortcut, but the AP readers maybe in May don't know that. And so I need you to be able to show all the steps for finding the derivative of that function there on your quiz. The second hint that I want to provide to you is on the back for number 3 and 4. I encourage you to find those lists of graphing connections and look through those very carefully. Look through lots of different examples that we put together in class. We actually drew one from the other. Be really careful about your concavity changes, your increasing, decreasing points, what that means for the derivative, and then vice versa for number 4, working backwards from number 4. So just be super duper careful. And then for number 5, we wrote a list of things that are not differentiable. And so you can just apply that list of things that are not differentiable for number 5. Okay, moving on to today's stuff. There's one thing I want to clarify real quick before we start trigonometry, and that is this. That sometimes you might see this notation. Okay, that is the derivative of tangent, and so that's taking the derivative of tangent. That is different from this. I do not want you to get confused because this is the inverse. Remember the arctan thing where you look on the unit circle to find where, where tangent of x equals this or whatever. So I don't want you to get this mixed up, that this stands for derivative. And by this I mean the tangent prime. Tangent, the little apostrophe tick mark there, versus tangent raised to the -1. This is tangent inverse, so the tan inverse. I don't want you to get mixed up on that notation, should you see that notation either in your textbook or on a test. Here we go. One of your response questions is actually to add to my list here. So reasons why sinusoidal graphs at trigonometry is important anyways. We know we did last year, we did a Ferris wheel problem where we modeled the motion of a Ferris wheel with sine graphs. These are my things, the real life scenarios of a sinusoidal graph, of a cosine or a sine graph. The reason I want to show you this is just to prove one more time, as if you need to be proved, this to be proven to you again, but just prove one more time that this trigonometry stuff is important. It is real life. It could be real life, depending on what your profession is going to be. I know that engineering, that trigonometry plays a big part in engineering, and of course in science, and all those wonderful things that you're going to grow up and be just brilliant people. And here's 3 examples. The end of a vertical spring, so if you were to drop something and it were to bounce up and down, kind of like bungee jumping. The marking of edge of a spinning disc, that would be the distance away from the starting point, so it would go out and then it would spin back around in, and then out and then spin back around in. Or just swinging an object from a chain, maybe like a grandfather clock. All of these things can be modeled using sinusoidal graphs. Now, what is derivative? Derivative is the rate of change of the real function. So what the derivative of sine, or the derivative of cosine, or any trig function, would be telling you the rate of change of these things moving. So the derivative would tell you how fast is whatever it is moving at that given point. So derivative is rate of change. These are the scenarios that you could model. If you took the derivative of that, it would tell you how fast the object is moving up and down. It would tell you how fast the object is spinning away and then moving back closer to you, or how fast the object is spinning from the left to the right. So trig can be applied wherever. I'm hoping that you have out the back of your blue sheet that you have these rules written in. We're going to work through just the regular trig graphs for now. The Inverse trig graphs, I'm still doing some reading up on those. I'm still not convinced. There's only a few of those that show up on the AP exam, and that's been modified this year, so I'm not going to worry about those yet. So let's worry about just the regular, simple trig rules. Hopefully you have the rules written down. We need to start paying attention to these rules here, these generalized, these chain rules. The majority of the trig derivatives that you're going to be asked to take are going to be following these rules. Not these simple, sweet rules where sine, the derivative of sine is just cosine. The derivative of cosine is negative sine. A quick way to remember where you put the negative sign is if you're going towards sin, then you're going in a bad direction. You're going in a negative direction. So that's the way I remember that. Tangent is secant squared. The derivative of tangent is secant squared. And you can read these. So, but what I want to pay attention to is I want to pay attention to these rules here. So what's important about these rules here is that it adds this little du dx on the end of it. So basically what these rules on the right are saying is not only do you take the derivative of sine and make it cosine, but you also take the derivative of the inside as well. This is going to turn into what we call the chain rule, where you work your way from the outside of the function in. So you take the derivative of the whole trig function, and then the derivative of the inside. That's what the du dx stands for all the way down here. The du dx stands for the derivative of the inside. So taking the derivatives of trig graphs, or excuse me, of trig functions, you work your way from the outside in. You're taking the derivative of every part of this trig function. Here's the way I like to remember it. You're basically working through these Russian nesting dolls. So you take your derivative of the big idea, and then you just work your way into the inside of the derivative, kind of like Russian nesting dolls. A quick example, a simple example, might look like this. I don't know if this is the next one or not. No, it's not. Good, yay. So if this was y, to take the derivative of sine, we know that the derivative of sine is cosine. Okay, first time through, you just leave it as it is. So, you leave the inside of the function as it is. So the first step here would be taking the derivative of just the trig function, and then working our way in, kind of like these Russian nesting dolls. So the derivative of the inside would be 2x. And there's nothing really on the inside of x. So this would be the correct answer. Not just cosine of x squared, but cosine of x squared times 2x. That's the derivative of the inside function. Let's practice some more. All right, to take the derivative of 3 cosine t2, we're going to apply that constant multiple rule, where the constant multiple really doesn't matter on the outside. We're just going to kind of let that hang out. Think about the Russian nesting dolls when you're taking the derivative of the trig function. So the derivative of cosine is negative sine of 2t. And now let's work our way inside. So the derivative of the inside would just be 2. This would be the final answer. You're more than welcome to write it like this, with the two multiples multiplied to each other and the negative sign on the outside. Very good. The derivative of this function here, cosine of 2x to the fourth, with the Russian nesting dolls, we're going to take the derivative of the whole thing, so that would be negative sine of 2x to the fourth. Notice I'm not touching the inside of the function until after I write that first initial derivative of the trig. Now the derivative of the inside, so 8x cubed, and there's nothing else on the inside of that x, so that would be the final answer. Working our way from the outside of the trig function in. Here's a souped up example. Woohoo! Let's take the derivative. Let's take the derivative working from the outside in. All right, so here we're working from the outside in. The constant multiple rule applies in that that 3 is going to come down here and hang out. Just kind of chill, wait for a second. All right, let's work our way inside this function. So tangent is the first thing we see. Tangent is the big, kind of like the big doll here, the big daddy here. The derivative of tangent is secant squared of x, and so I'm going to write that as secant squared of, do not touch the inside. Remember, the first time through, you write it just as it is. Times, now let's keep working our way inside this little nesting doll. So now I'm here. Times the derivative of this. So the derivative of sine is cosine of 2x. Still working our way in. the derivative of the very, very innermost part of 2x, the derivative of 2x is just 2. So you see these three steps here. I work my way through the tangent, I work my way through the sine, and then I work my way through the 2x. So that's the secant squared, the cosine of 2x, and then the 2. Simplified answer would look like this. It would be a 6 secant squared, excuse me, can't touch the inside of the function, so secant squared of sine of 2x times cosine of 2x. I work my way from the inside, I work my way from the outside in to the innermost part of this function. Kind of like Russian nesting dolls. Okay, that's super important when you're working through trig functions, working your way from the outside in. Now, applying that idea of working our way from the inside, from the outside in, let's get an idea here. Would the derivative of sine of 2x just straight up equal cosine of 2x? You know the answer because you just heard those first few examples. That no, the derivative of sine of 2x would actually be cosine of 2x times 2. All right, and then you can prove that to yourself here. Here's proof that we have to work our way inside in. I graphed cosine of 2x, and I graphed that alongside the derivative of sine of 2x, just to see if the derivative was equal to the cosine 2x. And obviously, it's not, because the derivative is this solid line. Oh my word, it has an amplitude of 2. Where did that 2 come from? We know, from the inside of the function. So the answer here would be false. The derivative of sine of 2x is not cosine of 2x. It's cosine of 2x times 2. Working your way from the outside in on these trig functions. Now what about cosine x squared? Is that derivative equal to sine of x squared? Same thing here. The derivative of cosine of x squared is actually negative sine of x squared times, work your way from the outside in, times 2x. And here's graphical proof that those two are not equal to each other. The answer here again would be false. The whole idea is recognizing that you can take cosine and move it into sine. Actually, it's negative sine. You can take cosine and move it into negative sine, but you also have to take the derivative of the inside of these trig functions. We're working our way to the inside of the trig functions. There is a special rule that I should have told you in limits about, since we're thinking about trig. There is a special rule that I need to tell you about sine of x over x. The limit is this: whenever, this is really random, but I need to just share this with you. Whenever you have sine of x over x and you're taking the limit as 0, it is always equal to 1. And the reason that this is a special rule is because this is also the case. See if you can catch this pattern right here. Sine of 2x over 2x is 1. The limit as x approaches sine of 7x over 7x is 1. You see what's happening here? You see the insides of these sinusoidals? So the limit as x approaches, and it only works for sine of x. It only works for sine. The limit is sine of pi x over pi x. You got it. It's 1. And the only reason I'm including this because I think I saw it on your homework assignment somewhere, maybe this coming time or time after that, but I wanted to just make you aware of this rule that whenever you have the limit as x approaches 0 at sine of x over x, or anything like this where the insides match the bottom of the fraction, the insides match the denominator, the limit as x approaches 0 there is actually 1. I want to prove this to you graphically here for a second. So graph the position and the velocity equations for this one. We can answer this because we just went through those examples. The limit as x approaches 0 is 1. But look what happens as it goes off to infinity. So if I've graphed sine of 2x, excuse me, all over 2x, you can see that it touches that 1 point there. It's not equal there at 1, but the limit is 1, so let's trace 0. Right there, you can see it's not defined, but the limit there is 1. But it is approaching 1 both from the left and from the right. Now what's happening as it goes off to infinity? I'm going to adjust my y value so you can get a better look at that. Let's go from -2 to 2. You see it's oscillating. It oscillates up to 1, and then it continues oscillating, but it oscillates closer and closer to that 0 value. So the limit as x approaches infinity, as it's going left and right to infinity, the limit as x approaches infinity is actually 0. I think the reason I'm including this is because I did see it on a homework assignment in a quiz and part of a test that's coming up. I want to just go ahead and make you aware of this rule, of this sinusoidal rule here, where it's the inside of the sine graph and the bottom of the sine graph. For the limit as x approaches 0, it's just 1. For the limit as x approaches infinity, is 0. That is true. That will always be the case when it's sine of something over that something. And that is it. That's all the examples that we would have done in class together. Of course, I can provide more examples when we come back together and meet again on Tuesday. However, for now, I would like for you to practice. You have to finish that quiz, of course. I'd like for you to practice a few of those out of your textbook. Don't do the entire homework assignment. Practice a few of the trig functions out of the textbook. Go back to that middle part of this video where I was doing the trig functions. And maybe just look at those examples again if you get stuck or if you need help. And then I'd like an email response. I'd like an email response from you about, first, what are other real-life examples that can be modeled by sine and cosine graphs? I want you to come up with one. I gave you 3 examples. You come up with another one. And the second one, how is taking the derivative of a trig function, like those Russian stacking dolls? I want you to put in your own words in an email response to me, please. So I look forward to getting your emails. I look forward to another class where we don't have to sit in lecture mode the whole time. We can, move around, play, work with each other. I'm excited. I hope you have a great weekend. Make good decisions, be good citizens, and do a lot of calculus. Bye, y'all.